in the previous class, we have learned about the shielding effect, uh, then the strength of the shielding effect, and also we have learned about the atomic radius and the ionic radius, and how this atomic radius and the ionic radius of this element has been changed according to the periods and according to the groups. That's actually we have learned in the previous class. So today we will learn about the electron ionization energy that is called that is uh, ionization energy. So this is actually designed by IE or the delta G. Okay. So first of all, we have to know that what is meaning of this ionization. Ionization means that we are doing ionized one element. That is the first point of the of this word. This is the ionization. So ionization meaning that means we want to ionize. We want to ionize an element. So ionized means that we can add these electrons and we can remove this one electron. So suppose consider this is a one type of metal. Okay, if I one electrons added, then it will be the anions. If I remove this one electron, then it will be the cations. So it is the ionization process. But when we are talking about the ionization enthalpy or the ionization energy, that means that removing a electron from an atoms or the ion. That means this is the second procedure. Okay, so the ionization here, the ionization enthalpy means that this ionization means that the removing a electron from an atoms or the ions. That could be the atoms or that could be the ions. What is meaning? Suppose I have the M, a one atom. We can remove this one electron, then it is form a M plus. Okay, so this is the atom. Okay, so from an atoms we are removing one electron. Similarly, what could be happen? Suppose I have a sorry, I have a this ion. I have a this ion. So from this ion, I am removing one electron. Then it will be have the two positive charge. So one electron could be removed from this atom, or it could be removed from this ion. So basically, that is the removing a electron from an atom or the ion. Now, the energy or this enthalpy, that means that delta G. So, ionization energy means that is the energy is the needed or the required to remove an electron from an isolated gaseous atom or this ion is called this ionization energy or ionization enthalpy. So, from this atom, suppose this is the iron. So, from this iron, easily one electron will be not removed. Okay, so we have to put one sufficient amount of the energy, then it will remove one electron and it will become this iron plus. Okay, so so to form to remove one electron from the valence shell or the outer shell of an gaseous or isolated or the ion, we have to put, we need this some amount of the energy that is called ionization enthalpy or this ionization energy. That is defined by this delta G or I of E. Third point is if the atom is neutral, the above defined ionization energy is called the fast ionization energy. So M equal to M plus plus of electron. So one electron is removed. So here, whatever delta G will be 1, so it will be delta G1. So this is the fast ionization energy because this first electron is removing from this atom. That's why this first electron is removing. That's why whatever energy is needed here, that is called the first ionization energy. Okay. So when this energy required to remove an electron from an isolated or the monovalent cation, if I remove this one electron from this monovalent cations M plus, then it will be from this M plus 2. But here this electron is removing from this monovalent cation. Then whatever energy is required, that is called the second ionization energy. Okay. Now the ionization enthalpy or the ionization energy is expressed in the units of the kilojoule per mole. So whatever energy is required, whatever energy is how much energy is required. Suppose it is the 5 kilojoule per mole energy is required. So this is the unit of this ionization energy or the ionization enthalpy. So ionization means removing one electrons from an atom, and ionization energy means some amount of the energy is the needed or the some amount of the energy is the required to remove this electron from the outer shell or the valence shell of an isolated and the gaseous atom, that is called the ionization energy. So you think about that some amount of the energy is needed. Okay, so amount we are giving the some amount of the energy from the outside. Okay, so this is one type of the endothermic process. Okay, exothermic process means that the energy will be the removed from the system. That will be the delta G equal to negative. But here, what is happening? To remove this one electron, we need this some amount of the energy. We have to give this some amount of the energy. So it is an endothermic process. So always, the ionization energy delta Z equal will be the positive value. Will give the positive value, and it will have the units the kilojoule per mole. So here the same thing, the first ionization energy. So this is the gaseous one atom. Uh, some amount of the energy we are putting here. Then the one electron is the removed. So whatever energy, whatever delta G1, that will be the first ionization energy. Then when we are removing the second electrons, this is the second electron, this is the first electrons from this gaseous cation, then it will be the delta Z2. So this is the first ionization energy, this is the second ionization energy. Now the question is that the second ionization energy or the second ionization enthalpy always will be the higher than the first ionization enthalpy. Why? That means that delta H2 greater than delta G1 always. Why? Because it is saying that it is a more difficult to remove an electron from a positively charged ion than from a neutral atom, because a cation has a greater effective nuclear charge than a neutral atom. This is the true. That means that suppose here is the X, this is the X class. So here the Z star and here the Z star 1. So here this effective nuclear charge is greater than this Z star 1 greater than 2. That's 1. So we will talk about in the next slide that how this ionization enthalpy is related to the effective nuclear charge. So when this cation is generated, that means that one electron is already less than the primary or the neutral atom. Okay, so the valence shell electron, suppose this one electron for that the X. Okay, so there is the one electron is also is there. There is the one electron is also is there. So for that X, if you just think about that, this is the nucleus is there. Okay, so we want to remove that electron. So here the distance is that one. So from that the nucleus to this outer shell electron distance is that one. But when it is the X positive, when it is the X positive, that means that means uh, we are talking about now that electrons. We are now want to remove that electrons. So this electron is very close to nucleus compared to that. So the effective nuclear charge on that electrons will be the higher than that one. That's why the Z star 1 greater than the Z star. Whence the effective nuclear charge will be the high, That means this nuclear pull, this nuclear, this nucleus actually, this attractions between this nucleus and this outer shell electron is the higher. Uh, then to remove these electrons, we need this higher energy. That means we need the higher the ionization enthalpy. Then the delta H value will be the high for that this X plus. So that's why this comment there it is written that the second ionization enthalpy will be the higher than the first ionization enthalpy. So this is a good point, and just remember that. Second point is that in the same way, the third ionization enthalpy always also will be the higher than the second ionization enthalpy. So there is the some factor uh, that already I have talked about the nuclear charge. Then the IE of E, that is the nuclear charge, when increases, then the increase also the effective nuclear charge. Okay, so when this effective nuclear charge will be the increase, uh, then the ionization energy also will be increase. So there is the another point is that size effect, size of the atom. Okay, so this ionization enthalpy that decreases as the size of the atom that increases. When this atom size is increased, when this atom size is increased, then this effective nuclear, then this ionization enthalpy value will be the decrease. How that will I will come later. Then the type of the electrons, this is the shielding effect is there, penetration effect also is there. Then another point is that electronic configuration. Some about this noble gas. Uh, they have the strong stable electronic configuration. So to remove this one electrons from that stable electronic configuration, we have to put the high energy. That means that then the delta H value will be the more high. Okay, so it is written here. This noble gas passes the very high value of this ionization enthalpy due to the stable octet configuration. It is a D8, uh, the 8 electrons is there. 1s2, 2s2, and the 2p6. That's why it is a octet is fluffed. It is a stable configuration. So it is a stable. So from that configuration, if you want to remove one electron, then we have to give the higher energy. It is a very difficult. So that's why the ionization enthalpy value will be the very high for this noble gases or any stable electronic configuration related metals or the atom. So now, how this size effect is actually dependent on moving from this across the period. When we are going to left to right, that means that period. Uh, when we are going to along the period, this the left to right, then the size actually that decreases. When this size decreases, that means that effective nuclear charge that gets stuck will be the increased. When it is increased, that means there is the attractions between this nucleus and this electron will be the increased. So this is the attraction. Also the increased. When this attraction is increased, then to remove this electron from this outer shell, we need this higher energy. Then the delta of H value also the increase. So it is written when this size that decreases, then the effective nuclear charge is increases. That's why this ionization enthalpy also increases along the period. Second thing, there is a two common or the two exceptional is that ionization enthalpy of this beryllium is higher than the boron, and ionization enthalpy of the nitrogen is higher than the oxygen because we know that nitrogen, oxygen, and then the beryllium and the boron. So we are going like that, but there is an exception is that according to that rule, oxygen should have the higher energy enthalpy than this nitrogen, but the nitrogen for the nitrogen, ionization enthalpy value is higher than the oxygen, and in case also the beryllium is higher. So this is the exceptional case, but the answer of this we will be discussed later end of this class. Now, when we are going to this moving the down group, that means we are going to this, suppose hydrogen, lithium, sodium, potassium, rubidium, cesium, like that. So when we are going to this up to down, then what is happening? Then size is increased. When this size is increased, then what is happening? Then the Z star, this effective nuclear charge, if you see, the Z star value actually almost constant. It is almost constant at 2.2 around that. If you check in our previous class, already I have discussed that when we are going to this down the groove, uh, then the n equal to 1, here n equal to 2, then n equal to 3. It is like that actually. It is happening here also. So, so the principal quantum number is increased. When this principal quantum number is increased, then number of also electron in the inner shell also the increase. So that is actually happening here. The number of cell also increase and the atomic size also increase. But there is an increase in the number of the inner electrons, which actually seals the valence shell from this nucleus. So when what is happening, just think about that. This is for I am just talking about the sodium. Okay. So here is an electron, here is a nucleus. So here the suppose the 5 electrons is there. For example, this is a 5 electron is there. When we are going through this moving down the groove, then the number of electrons of the inner shell uh, is increased. Suppose there is a 10 electrons. So when this number of electrons is increased here, then this electron actually shielded that electrons from this nucleus. So when this electron, number of electrons actually shielded that electron from this nucleus, then this attractions between this electron and this nucleus is the decreases. That's why actually Z star is constant. That's why actually electron affinity, ionization enthalpy or the ionization energy will be the decrease down the group because large number of electrons is increased. When this large number of electrons is increased, then shielding effect also will be the increase. This sigma value also that will be increased. When this sigma value increase, then this attraction between this nucleus and this electrons will be the decrease. When this attraction is decreased, then the ionization energy or ionization enthalpy will be the decrease down the. So this is the fundamental thing how actually this ionization enthalpy or ionization energy is decreasing or the increasing according to this atomic size or the moving the down the groove and the, if you're going to this period. Okay, so this is the trend. This is the trend of this ionization enthalpy. How it is really correlated with this atomic size and and also how it is the correlated with this jet star. This is effective nuclear star. So here we can see easily that from the down the group, this is the hydrogen, lithium, this is the sodium, this is the potassium. The ionization enthalpy value is decreasing. So that means that to remove the one electron from this potassium, okay, is very easy than the sodium, than the lithium, than this hydrogen. Okay. Similarly, if you go to this left to right, okay, if you go to this left to right, then this ionization enthalpy value is increased. It is increased, and this is actually decreased. Okay. So when we are going to this, suppose magnesium to aluminum, then the silicon is increased, then phosphorus is increased. So this actually trend defined that to remove the one electron, to remove this one electron from this phosphorus, very difficult than the silicon than this aluminum. So ionization energy means that this is the sum amount of the energy. This is the needed energy uh, uh, to remove one electron uh, from the valence shell of an atom. So this amount of the energy is needed actually to remove this one electron. So this is the ionization energy and this is the ionization enthalpy we can say. Now this question is here. This is the ionization energy of this beryllium is higher than this boron. Now the question is the why. If you see this periodic table, sorry, this the trend. Here this is the beryllium. Here this is the boron. This beryllium has the higher ionization enthalpy than this boron. But if you see the periodic table, uh, here the beryllium has the electronic configuration 1s2 and 2s2. Okay, 1s2, 2s2, 4 electrons. And for this boron case, if you see this one electronic configuration 1s2, 2s2, and this 2p1. So here the valence shell is p orbital. Here the valence shell is s orbital. Now there is a two reason. First reason is that this is the p1. That means the p orbital has a one electron. If I remove this one electron from this p orbital, then it will have this electronic configuration 1s2. All these s orbitals are filled up. It is a stable configurations will be formed for this boron. If I remove this one electron from this p orbital. So, but for this beryllium, this is a stable configuration. 1s2. Already two s orbitals are filled up. Okay. So from this configuration, if you want to remove this one electron, it's very difficult. So to removing one electron from this p orbital is very easy than 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 beryllium case. This is the first reason. Second reason is that for this s orbital has a more penetration power, more shielding effect than this p orbital. This is actually written here. The electronic configuration, this is for the boron and this is for the beryllium. But the penetration of this s orbital or to this nucleus is the more than that of the p orbital. Okay, so what is happening here for this beryllium case? S orbitals is the more penetrated to the nucleus, but the p orbitals is not penetrated, not too much penetrated like the s orbital. But if you see for this beryllium case, outer shell electron is present s orbital, and s orbital has a more penetration. That means this electron, this one electron is more close to this nucleus. That means there is a more attractions between the nucleus and these electrons. That's why, that's why remove this one electron from s orbital for the beryllium case is the more higher than boron, because here this one electron is present in p orbital, but we know that p orbital has a less penetration than the s orbital. That means that this electron is more far away to the nucleus compared to the beryllium. So to remove this one electron from this p orbital is very easy. That's why the ionization enthalpy of this boron case is less than beryllium. It's written here. So this is the p orbital. Hence the p electrons of the boron is more shielded than the nucleus, and this is the inner core of this electron. So s electron of the beryllium. So therefore it is easy to remove this p electron from this boron compared to this removal of the 2s electron from the beryllium. That's why boron has a smaller mass ionization energy than the beryllium case. So this is a question how you will explain. First of all, you can explain according to the electronic configuration. Second, you can say the penetration power of the s orbital is greater than this p orbital. Okay. So when the electron is present in the s orbital, that means this is the more penetration. The more penetrations of this s orbital, electron is the more close to the nucleus. But for the p orbital, is the less penetration. That's why this nucleus is the less close to the nucleus. For that boron case, there is the shielding effect is there. When the shielding effect is there, that means this effective nuclear charge will be the less compared to the beryllium. That's why this electron should be very easily removed. For that boron case, it will be easily removed compared to the beryllium case. That's why it has the smaller ionization energy or the enthalpy compared to the beryllium. Now the second question is that why this nitrogen higher than more ionization energy, nitrogen higher than this oxygen? Because here if you see nitrogen also the 2p orbitals, this outer shell electron is present in the 2p orbital and oxygen also has the outer shell in the 2p orbitals. So here there will be the no penetration involved. So here is the involved of the electronic configuration. For this nitrogen, the electronic configuration is 1s2, 2s2, 2p3. That means it is like that actually. 1s2, 2s2, and this is the 2p3. And for that oxygen, it is the 1s2, 2s2, 2p4. So this is the electronic configuration like that. So from the two electronic configuration, easily we can say this is a stable electronic configuration because it is a half field. That's why it is a stable electronic configurations compared to the oxygen electronic configurations. So if I remove this one electron from that electronic configuration, then it will gain this half field electronic configuration. Then it will be so to remove this one electrons will be the very easy for that oxygen case. But here is a half field, it is stable. So to remove this one electron from the stable electronic configuration or the half field electronic configuration is a very difficult compared to the others. So there's the two electrons of these two p orbitals is occupy same the p orbital resulting in increased electron repulsion. Here the electron repulsion region is there. Consequently, it is easy to remove the fourth 2p electron from this oxygen than it is. So to remove the one electron, this is nitrogen. So I have explained this question, this answer according to this electronic configuration. You can explain the electron repulsion also. Now we will know now about this electron gain enthalpy. So electron gain enthalpy. That means we want to give the one electron. Now we want to add this one electron. Electron ionization energy or the ionization enthalpy means removing one electron. But electron gain enthalpy, that means we want to add one electron. When we want to one electron to the valence shell of an atom, then some amount of the energy always will be the removed from this atom. So here, this energy will be the removed. Electron is coming to this atom, some amount energy is removed from this atom. This is the electron gain enthalpy. So some amount of the energy is coming from this atom side. Okay, so it is an endothermic process. So here, this electron gain enthalpy always will be this endothermic. So that means it will be always positive. Sorry. It will be the exothermic process. It will be the always the negative. So here it is written that when an electron is added to a neutral gas to the converted it to this negative ion, that means suppose this is the X. If I add this one electrons, it will be the X minus. So it is an anion and it is a neutral. Okay. So here I am one electron is adding to this neutral atom, then it is forming an anion. Okay. So then the some amount of the energy will be the removed. Then this energy is called electron gain enthalpy. This electron gain enthalpy provides a measure of the ease with which an atom they add an electron to form an anion as represented like that. So here X a first electron is there. When it is the one electron is coming to this gaseous atom, it is form an anion and some amount of the energy is the removed. So that's why this delta is the negative. It is a exothermic process. It is an exothermic process. So that's why it is a negative. Always. Depending on the element, the process of adding electrons to these atoms can be the either endothermic or the exothermic. But for the many element, the energy is released. When an electron is added to this atom, then the electron gain enthalpy is the negative. So it is an exothermic process. Again, it is an exothermic process. There is some factor. First factor is that effective nuclear charge. With the increase in the effective nuclear charge, the force of the attraction extracted by the nucleus on and the electron increases. So consequently, the atom has a greater tendency to attract the additional electron. That's why it will be the more negative. What is that? There is the more negative and this is the less negative. It will be the negative value. But more negative, when it is the more negative value, that means easily electrons added. More negative value, that means easily electron added. Less negative value means that it is not easily electron is added. Very, very difficult to add an electron. Huh? So more negative value when we are comparing these two electron gain enthalpy, if you see that it is giving the more electron negative value, that means easily one electrons will be added to the valence shell of this gaseous atom. But when the electron effective nuclear charge increase, what is happening here? Effective nuclear charge, when the effective nuclear charge is increased, then it has a greater the tendency to attract this additional one electron. So it will so easily one electrons will be added of this to this valence cell. So then it will give this more exothermic process. That's why it will have the more negative value. Now this atom size, with decrease in the size, when the size is decreased, then this effective nuclear charge is increased. We know that when this effective nuclear charge is increased, then this electron affecting electron gain the enthalpy, that value also the increase. It will have the more negative value. Second point is that electronic configuration. The value of the electron gain enthalpy depends effectively upon the electronic configuration of an atom. And elements with the stable electronic configuration possess the lower. That means that suppose one electron, say neon, argon, krypton. So this actually noble gas. So this noble gas has a octet filled up, has the stable electronic configuration. So if I added this one electron for that noble gases, then it will easily, then these electrons will be not easily added. Then it will have the less negative electron gain enthalpy value. Okay, that means that when the electron is easily added, then the electron gain enthalpy will be more negative. When it is not easily added, It is very, very difficult. It is facing the difficulty. Then it will have the less negative electron gain enthalpy. Noble gas have a particularly zero and a positive electron gain enthalpy because they have the no tendency to gain an electron because it has its stable electronic configuration NS2 and NP6. That's why, that's why this type of the element not wants to one electron to our valence shell. Then it will show the zero electron gain enthalpy or it will show the positive electron gain enthalpy. But if you see this halogen, halogen has the electron affinity is the more high. That means halogens always wants the one electron to their valence shell because it has electronic configuration. If you see for this P5 always, if the one electron is added, then this electronic configuration will be the P6. It is the octet filled up and it will follow the octet rule and it will have the stable electronic configuration like the mobile gases. So that's why the halogens will have the high negative electron affinity. Uh, Now there is a some range of the electron gain enthalpy. So here if you see in a preview, so when we are going from this left to right, this is the left and this is the right. What is happening here? The size factor is there. The atomic size is decreased. When this atomic size is decreased, then the effective nuclear charge will be increased. When this effective nuclear charge is increased, then this element will have tendency of the attraction of an outer electron towards the nucleus. Then this electron gain enthalpy will be the high. It will show high negative value. In a period, the electron gain enthalpy is increased because becomes the more negative as well as we move as a across a period because the atomic size decreases. Hence, the force of the attraction extracted by the nucleus on the electron, that means the jet star, effective nuclear charge also the increase. Consequently, the atom has a greater the tendency to attract the additional electrons. That's why this electron affinity is increased. Similarly, in a group, if you go up to down, then the, the atomic size is increased. When this atomic size is increased, atomic actually the principal quantum number is increased. When this principal quantum number is increased, then this inner cell electron, number of this inner cell electrons also the increase. Then the shielding effect, uh, there is a positive, there is a outer cell electron. Then the shielding effect also the increase. There is a wall of this electron. When this wall is the more stronger, when this shielding will be the more stronger, then this coming electron, this is the suppose the coming electron. So the attractions of this nucleus on this coming electrons will be the decrease. Then the electron gain enthalpy also the decrease. So it is because the atomic size increase, therefore the effective nuclear attraction between this nucleus and this coming electrons will be the decrease. That's why the electron affinity also the decrease. So in a period, this value actually will be the increase. It will give the more negative value and it will have the less negative. So this is the table where we can see easily, where we can see easily that when we are going, suppose for that case, the sodium, you see this one, two, three. This is the three. Third pure. If you see this third pure, when we are going to this sodium to ammonia, then the silicon, then the phosphorus, then the sulfur, and the chlorine, and this argon. So this is actually it is not showing. This is actually the stable electronic configuration. That's why the electron gain enthalpy here equal to 0. Or that magnesium also is 0. But if you compare this aluminum to silicon is increased, then the phosphorus also the decreased. But from this phosphorus to sulfur also the increased, sulfur to fluorine also the increased. So there is a trend of this electron enthalpy, the increasing value. But there is a some exception. But if you see the along the group, if you go to this up to down, then this hydrogen is minus 70.8, lithium is decreased, sodium also decreased, potassium, rubidium, cesium, always the decreases. Because the size increased, inertial electrons, number of the inertial electrons also the increased, shielding effect is increased, then the attractions of this nucleus on this upcoming electron, this attraction actually decreases. When this attraction is decreases, then the electron gain enthalpy value also the decreases. And this is the fast ionization enthalpy. We are talking about here the fast electron gain enthalpy. Okay, one electron, first electrons, it is adding. So this is the some value here I am I am showing actually I am showing that how this value actually decreasing and increasing. But there is the some exceptional. You can see that for that oxygen and this fluorine. If you compare this value for that oxygen minus 141.0, but for this fluorine case, no, sorry, for the sulfur case, if you see this value is minus 200.4. But if you know, but we know that when we are going up to down, then this value is decreases. Here, but here for that oxygen case has the minus 141.0, but for that sulfur case, it is showing minus 200.4. But it is the increases. It is increases. For that fluorine case also. Fluorine case, for the fluorine has the minus 200, sorry, 328.0. For that fluorine case, it is the 349.0. It is the increases, but it should have decreased value. It should have the less value, less negative value. But for that case, there is a exceptional between the fluorine and the chlorine, between the oxygen and the sulfur. But the question is the why. Question is the why it is showing this type of the exceptional case. This is the reason. এখন আমি এখন ব্যস্ত আছি আর পরে বলবো না না মেজর স্টুডেন্ট আমি বাইরে আছি আমরা না না হয়নি sorry for that. Now here is the question that electron gain enthalpy, the electron gain enthalpy of this oxygen is less than sulfur. Similar question is that electron gain enthalpy of that fluorine is less than the chlorine. But question is that why? Because the electron gain enthalpy of the oxygen and the fluorine is less than that of the succeeding element. This is because when an electron is added to this oxygen and the fluorine, the added electrons goes to the polar n equal to 2. This is the n equal to 2. For that case, if you see, this is the n equal to 2, but this is the n equal to 3. Okay, so this is n equal to 2, quantum level, and suffer the significant the repulsion from that electrons. Because n equal to 2, that means there is the 2 cell, 2s2, and this is the 2p, s orbital, and this is the p orbital. Okay, but when we are talking about the n equal to 3, then there is the s, p, and d orbital. When n equal to 2, then s and the p orbital. So one orbital is always missing. So when we are adding this one electron for that n equal to 2, then there is the electron to repulsion will be there because the place is very very small. But here there is the lots of place. There is the d orbital also is there. So there will be the no repulsion. There will be the no repulsion electron to electron. There will be the no repulsion. So that's why actually to add one electron uh, oxygen and this fluorine is a very very difficult actually compared to this sulfur and this chlorine. So that's why actually electron gain enthalpy of this oxygen is very less than sulfur, and that of the fluorine case it is also the same. Now we will talk about the electronegativity. Electronegativity and electron gain enthalpy. There is a similarity. Electronegativity also that the tendency of an element in a molecule to attract the shared pair of an electron towards itself, known as electronegativity. So, electron gain enthalpy, what was the electron gain enthalpy? Electron gain enthalpy, that means this is a metal, we are adding one electron. Here, we are adding one electron. This is called the electron gain enthalpy. Adding one electron. Okay, from the outside, this is called the electron gain enthalpy. But electronegativity, that means suppose X and Y forming a covalent bond. That means the covalent bond means that 100 electrons pair will be shared by the X 50%, also is shared by this Y 50%. But when this electronegativity of this X is the higher than this Y, then it will share 80%, will share that 20%. When electronegativity of this X is higher than this Y, then this electron will be the shared is more by the X. Then what will be happened here? This bonded electron pair will be here. Then it will be the more negative charges. It will be the delta negative. It will be the delta positive charges. Because because here fully not one electron is coming to the X. Here what is happening? This X has a more electronegativity than this Y. That's why it will not shared by the X. Okay, so it is actually written here the tendency of an element in a molecule to attract the shared pair of electron towards itself is known as the electronegativity. It is measured on the Pauling scale, in which the fluorine it is a most highest electronegative element. Uh, its value attributed to a value of 4. Now in a group, if you see, same thing is here. In group, so Z is increases, Z star is effective nuclear charge, almost is the remaining the constant, but number of the cell increasing, the atomic radius also the increasing, force of the attractions between of the electrons and this nucleus also the decreasing, so the electronegativity decreasing down the. So when we are going the up to down, huh, then we know that atomic size is increasing, n value also the increasing, and this inertial electrons also the increasing. That means that is the shielding effect. This shielding effect is increasing. So this effective nuclear charge, this is the Z star, the constant. That means when the shielding effect is increasing, then the attraction between this nucleus and these electrons also the decreasing. That means this electronegativity also the decreasing down the. But in a period, it will be the opposite. Z and the Z star effective nuclear charge is increasing. Number of the cell is remaining constant. At is equal to 2 by equal 3. Atomic radius is decreasing. So the force of the attraction between the shared and electrons and the nucleus also the increasing. So the electronegativity also increasing along the period. When we are going to this left to right will be the increasing. So this is actually there is a some value. You can see that when we are going to this hydrogen to lithium, then sodium, then potassium, then rubidium, then cesium. When this atomic number is increasing, when we are going to this along the group, then this electronegativity value is decreasing. But when we are similarly, when we are pure, this is the one pure, the second pure, fluorine, krypton, xenon, radon. So when we are fluorine, the krypton. So here also the decreasing. Here also the decreasing. So this is actually some value and some strength of this element of the electronegativity value. of this element is given here. So here I will stop this class. So here already I have taken the four class. So in that four class, up to electronegativity, I have taught. In the next class, I will talk about the reactivity of this element, and I think the fifth class will be the last class of this chapter. Thank you very much.